All right, so example 9 is starting by saying to hold on to your homework, right? Those of you who have started your homework, right? Some of y'all started the morning of, but it's due. Did y'all see that there is an asteroid/meteor that is heading towards planet Earth? It's going to be coming by us on February 5th or somewhere around there before the government shuts down. When is the Superbowl? February 4th? Okay, yeah, that's right, February 4th. I'm not sure when the meteor's supposed to come. Maybe it's supposed to come on the 4th or maybe the 3rd. I don't know the exact date. But I know that there's some people that hate Philadelphia and New England, and they're hoping that the asteroid hits Earth so neither one of them wins the Super Bowl. That's kind of going to extreme. I think we're safe. I think the people who are monitoring it is safe, so we don't have to call up Bruce Willis and send him up there to save us. But they said that it's traveling through space at 67,000 miles per hour. That's kind of you would get a ticket and land a park, right? If you're moving that fast. You know what? We should probably look it up since we're recording. Asteroid to hit Earth, 2018. Ooh, there's one for 2019 and 2036. Apparently, Google is suggesting. There we go. Let's talk about the big scary asteroid that's not, look at that, all caps, going to hit Earth. Look, there's a photograph of it. Someone is traveling behind it and taking pictures. And there's a big white spot there. Earth has a melatonin problem. The asteroid's name is 2002 AJ129. 129. Look at that. In fact, it's predicted to get no closer than 2.6 million miles from Earth. Okay? Yeah, so that's pretty good. See, it's traveling at 67 miles per hour. Yeah. Ooh, there's a better photograph of it. Now you can see the wind behind it that shows 67,000 miles per hour. See that? All the dust falling off it. Oh, not 67. You would still get a speeding ticket at 67 in Atlanta Park. It's like a third of a mile wide. So these things happen all the time. It's nothing to lose sleep over. But that's moving out in space. Okay, so now what we're going to do is we're going to figure out approximately how fast Earth is moving around its orbit around the sun. So the Earth is traveling in an elliptical orbit, but of all the orbits, the Earth's orbit around the sun is the one that is pretty much most circular. It is not perfectly circular, so it is an ellipse. Now, an ellipse has two centers instead of just one like a circle. We call them foci. The sun is at one of the foci, or one of the centers, and there's really nothing at the other focus or center. So the Earth travels around, and it actually moves faster as it approaches the, I think it's called the Perihelion, which would be this point over here where it's closest to the sun. And then it moves slower over here when it's at the ahelion. So it doesn't even move around its orbit at a continuous speed. But we're going to assume two things here. We're going to assume the Earth moves around the sun at a constant speed, and we're going to assume that it moves around the sun in a circular orbit. Two big assumptions, right? So here's what we want to do. We want to figure out then how fast is the Earth moving around that circular path. And of course we know, then we'll call that part A, that's the linear velocity formula. So the linear velocity of an object, v, that moves around a circular path is equal to the radius times the angular velocity. So because we need the angular velocity, let's go ahead and go off to the side and figure out what that is for the Earth. Okay? Remember, the angular velocity is some measure of rotation per unit of time. The Earth makes one rotation around the sun, how often? Very good, 52 weeks. We'll go with it, right? All right, 52 weeks. Now, we want to figure out how fast the Earth is moving around the sun in units that we kind of appreciate. Feet per second is not bad, but the speedometer in your car is something that you'll probably have a better appreciation for. It measures it in what? Miles per hour. So we want to actually convert the angular velocity to radians per hour. We want to convert it to radians per hour. So if we started with one rotation every 52 weeks, I like that. That's nice. Then we have a little bit of dimensional analysis to do over here to get to where we want to go. So let's get rid of the rotations first. One rotation is how many radians? Very good, 2 pi. Very good, 2 pi. So that gets rid of rotations, and now we have weeks, and we want to get from weeks to hours. Oh boy. So we got weeks up here, and I don't know if we can go straight to hours, so let's put days down here. How many weeks in a day or days in a week? Let's sing it. Monday, Tuesday, Wednesday, Thursday, Friday. I think 7, right? 7? Yeah. In 8 weeks. No, why did I put 8 there? 1 week. 1 week. You'd lose points in an English class for that, right? 1 week. 1 week. 1 week is 7. Let's call that 7 day. There we go. We have no idea what plural is. 1 week is 7 day. That's good enough for us. So let's see. Now our weeks are going to divide out, and we need to get from days to hours. So we got days in the top, and then hours in the bottom, and of course 1 day is 24 hours. So thank you, Johnny, for giving us 52 weeks. It gave us a little bit of an adventure getting to the units we wanted. So now we have radians per hour. All right, so let's go ahead and figure out what that is. Go to the calculator and type that in. So I'm going to leave pi visible, and it's because we're going to use that for a subsequent calculation. So I'm not going to multiply pi in. I'll just say it's 2 divided by 52 divided by 7 divided by 24. And then I'll hit math, enter, enter. Whoa! So the angular velocity then of the Earth is pi, because it's 1 times pi, over 4368 radians per hour. All right, so when you write that down, that's not our final answer, so we'll leave it like that. Now with radians per hour, it's going to make the calculation easier for what we want. We want to know how fast the Earth is moving around its orbit. So what is the radius of the Earth? Well, we're assuming it's perfectly circular. The average distance from the sun, you may know from the They Might Be Giants song, right? The sun is a massive incandescent gas, a gigantic nuclear furnace. Have you heard the song? No? Okay. But you've heard the Monday, Tuesday, Wednesday, Thursday song, right? Yeah, preschool. 93 million miles. That's good to know. We're 93 million miles away from the sun. So that's the radius. Wow. So now I'll go ahead and say 93 million miles. Got to keep track of all my zeros there. And I'll put units, that's miles, times pi over 4368 radians per hour. All right, what are our units going to end up being? What's miles times radians? Miles per hour. Good. So if you wanted to, you could have just said it was 93 million miles times 1 rotation over 52 weeks, and you could have done all of these conversion factors in this calculation. That would have been fine too. All right, so let's go ahead and type it in now. Since I have this number here, I'll just go ahead now and say I'm going to take that number and multiply it by 93 million. That's 6 zeros times pi. And that gives me 93 million pi divided by 468. And you get this answer right here, 66888.305 miles per hour. Now, for a calculation like this, maybe it's not best practice to go to 3 decimals, right? Because we're kind of making a couple of assumptions about constant speed and circular orbit. But we could say then maybe, if you wanted to, about 67,000 miles per hour, somewhere in there. About 67,000 miles per hour. How fast was the comet going? Or the asteroid, I should say, that's supposed to almost hit us 2 million miles away? It was going about the same speed, right? So if you line them up for a race, who would win, the asteroid or Earth? I don't know. It would be a photo finish, wouldn't it? It would be a photo finish. That's just unfathomable, right? You're sitting at your desk right now. Hold your arms out. Do you feel it? Do you feel us moving through space right now at 67,000 miles per hour? What if you put your hand out the window? Like when you're in a car, you don't feel it, but you put your hand out the window and, right, it blows back. Can you put your hand out the window there, Means? No, not without breaking it. You're a good man for not breaking my window. Is that why it's windy outside when you go outside and it's windy? Is that because the windows are down and we're traveling through space? Y'all don't feel that, right? 67,000 miles per hour is how fast we're traveling through space on this giant terrestrial ball we call planet Earth. It's quite a ride. Okay, cool. But that's not the only thing that makes this ride awesome. One of my favorite rides at the Comal County Fair is the Zipper. I like the Zipper. Yeah. But also there was one back in the day called the Sizzler. The Sizzler. You know what the Sizzler was? It looked like this from an aerial view. You had several arms, looked like that, and it rotated. The arms rotated like that. But on the end of each arm, you had a car that also rotated. Okay, so it was like double rotation. And if you sat right here on the outside, everybody who sat next to you would, boom, they would slam into you and pretty much break your hip. There were a lot of accidents. Because as you went around, you felt these double G's of rotating in a circle while you're spinning. It's kind of like the teacups at Disney World. Maybe more of y'all have ridden those. It's kind of the same idea. The whole thing is spinning, but while you're spinning, you're also spinning on a tighter radius. So every once in a while, if you can hit, the back end while it's turning, you can experience both G's. And it's kind of thrilling, right? The thrilling spinning teacup ride. So that's kind of what Earth is. Earth is doing the same thing. It's going around this circular path around the sun at about 67,000 miles per hour. All the while, it's rotating on an axis, right? Okay. So now we want to figure out how fast is the Earth spinning on its axis. That'd be good to know. So that is another V equals R omega problem. We're spinning again. So now the velocity around its own axis is going to be the radius of the Earth. If you zoomed in here, you need the radius of the Earth. And again, it's pretty good if y'all would know what the radius of the Earth is approximately. 78 miles? No. What is the radius of the Earth approximately? 3960 is good. If y'all remember about a little less than 4,000, that'd be good. That'd be good. So that if someone walked up to you on the street and asked you the question out of the blue, you wouldn't look like an idiot, right? You're a member of planet Earth. It's kind of good to know its relative size. We're going to use 3960. Of course, the Earth is not perfectly round, so we're making the assumption again. So 3960 miles, and now we need to come up with a different omega. It's not the same omega here. So unlike the other one where I found omega first and then plugged it in, we'll go ahead and do the conversions right here in the calculation. So we need to start with some common knowledge about the Earth rotating now, not around the sun, but on its own axis. And we want to end up with hours. So the Earth makes one rotation around its axis every 24.5? Is that a half an hour every other day? Every day is a half an hour more? Is it? Okay, I don't ever experience that. I'm just going to go with 24 hours. We'll go with 24 hours. There might be some decimals there, right? But that's a conversion most of us know, right? The sun comes up, the sun goes down. The sun goes up, the sun comes down every 24 hours. Unless you live in Alaska, right? Then it's like the sun comes up and then, dang, it's hard to go to sleep. And then the sun goes down. And then the sun comes up again. That's Alaska for you. All right, so if we multiplied right now, what would we have in the numerator for our units? What are miles times rotation? What? Yeah, miles times rotation is Miles rotations. Very good. We don't want that, right? So this is like the number one mistake that students make. They think that rotations are like, there's no unit of rotations. Yeah, there are. It's called rotations. You need to convert rotations to radians. So one rotation is 2 pi radians. Now, if you want, you could just say that this conversion factor is 2 pi radians over 24 hours, and that would prevent you from doing another conversion factor. Okay, but sometimes conversion factors are fun, which is why I was delighted when Johnny gave us 52 weeks for the length of a year. Okay, so rotations divide out, and now we're left with miles times radians, which is, in fact, just miles divided by hours. So now we know that's going to work. So now we go to the calculations. Before we get to that, does anyone happen to know, just off the top of your head, about how fast we're spinning? This is if we're on the surface of the Earth, right? We have to be on the surface of the Earth for this number to work. We can't be like in the middle of the Earth where all the molten magma is. Anyone know off the top of your head? Yeah, okay, really fast. Do you think it's faster than 67,000 miles an hour? Well, let's see. 3960 divided by 24 times 2 pi. Come on, big bucks, no whammies. That's a puny number. So again, because we're making some assumptions, maybe, 3 decimals is not quite the best number here. So we could say squiggles, let's just say about 1,000 miles per hour. So now you know. You have information now that you can share with loved ones around food. Okay? Talk about how fast you're spinning and just be amazed that the food is not flying off the table as you're eating it. You're traveling through space around the sun at 67,000 miles per hour approximately, keeping pace with the asteroid, while you are spinning in a tighter radius at 1,000 miles per hour, right? And so just like on the Sizzler, sometimes if you hit this point right here, as you're coming around this circle here while it's spinning, if you can hit both of those at the same time, that's why people on planet Earth throw up, because they hit that at the same time. And maybe they've had way too much to drink, right? Don't do that, folks. Okay. All right, so there you go. Good information. Good information to know. All right, so now without looking, me looking or you looking, what's the approximate radius of the Earth? Yeah, about 4,000 miles, 3960, a little less than 4,000 miles per hour. How fast are we traveling around the sun? Around 67,000 miles per hour. How fast is the asteroid moving? About the same, right? About the same. It's traveling on a different path, so that's why it's not like our twin, right? It's not like they're all the time. And then how fast are we spinning around the axis? About 1,000, right? Does anyone know the degree tilt of the axis? It changes, right? It changes. The average angle, though, of the tilt, here would be the North Pole and the South Pole. 20, 25, 24, 27.5, 24.5. Yeah, it changes. What is that called when it wobbles? There's a specific term. Prolation, pronation? I don't know. Pronation is when your feet turn inward. Maybe it's prolation. I don't know. But there's another application of an angle. We're tilted on the axis. So anyway, good stuff to know. Good stuff to know. So think about that next time when you're doing your math homework. Make sure it doesn't fly away, because once it goes into space, it's done. And yeah, I've never had that excuse. My dog ate my homework. My homework blew away and drifted into space. I just wasn't paying attention, and it caught the wind. All right, you can turn it in tomorrow for full credit. Thank you. All right. Comments or questions on that? You're learning. You're learning things. If not math, you're learning facts. All right, example 10, the last one. We've only got 20 minutes left to do this problem. Yes, sure, absolutely. I better stick more to the task at hand instead of doing all these going off on tangents and stuff, or we risk not finishing. All right, a bicycle. A bicycle is a cycle that has two. A bicycle, right? Bicycle, right? Yeah, a monocycle is one cycle. A bicycle is two cycles, right? All right. Y'all have seen bicycles before. Okay, so a bicycle has a pedal sprocket, also called, I don't know, a gear. It has I like sprocket. It's fun to say sprocket. It's a good word. So a bicycle has a pedal sprocket with a 9-inch diameter, a wheel sprocket with a 3-inch diameter, and a wheel with a 29-inch diameter. If the bike is being pedaled at 35 RPM, how fast in miles per hour is the bike traveling down the road? So this is kind of like the one with Mrs. Lincoln. Let's go ahead and draw a picture, and don't make fun of my bicycles. There's the bi part of the bicycle. And then let's see, I'll pick a different flavor here. There is the pedal. Here are my pedals. Well, not like that. Maybe like this, like that. And then you have a wheel. We'll make the bike go this way. There we go. This one's going to be a little bit smaller back here, but the bike is going that way. And of course, they're connected by some device, whether it's a chain or some kind of cable or pulley or whatever. So let's go ahead and start labeling things. The pedal sprocket is a 9-inch diameter. So this is 9 inches right there. The wheel sprocket on the back is a 3-inch diameter. So I don't know if I could draw that in there, but we'll call that one 3 right there. And then the wheel itself is a 29-inch diameter. So notice that the wheel and the back sprocket, they share an axle, right? So that's a 29er right there, and that's kind of the new fad in mountain bikes. We're pedaling at 35 RPMs. So this thing right here is going around at 35 revolutions per 1 minute. And based upon how fast this thing is being pedaled, I want to know how fast this thing is moving down the road in a straight line distance. All right, so how are we going to figure that out? Well, first of all, I need to somehow translate the linear velocity down the road to something on a bicycle, right? So because the energy is being transferred from the pedal gear to the back wheel gear, which is then being transferred to the tire, ultimately, I want to figure out how the linear velocity of a point that is on the edge of the tire, because that's what's touching the ground. So if I could figure out the linear velocity of that thing, how fast it's turning, I will be able to then figure out how fast it's moving down the road, just like we do at Mrs. Lincoln's problem. All right, so let's go ahead and begin with the end in mind. I'll just use that little dot there. I want to know the linear velocity of the tire. I'm going to start labeling this. That's ultimately what I want to know. Well, that's going to be the radius of the tire times omega of the tire. Right? Do you agree? Okay, but I don't know that. All I know is how fast the pedal is spinning. So let's go ahead and list what we know. I have it up there, but I'm going to list it down here. Omega of the pedal is 35 revolutions per 1 minute. Let's just keep it in RPMs for now. It would be a little bit easier. All right, so how am I going to get then from the linear velocity of the pedal, or the angular velocity of the pedal, to the angular velocity of the gear on the back? They have different angular velocities, right? That's why when you have different speed bikes, you can switch this back one to gears of different size, or sprockets of different sizes, and you get different gear ratios, and they spin differently. What do the back wheel sprocket and the pedal sprocket have in common? What do they share? They share the same linear velocity. Excellent. That's important. They're connected literally by the chain. And that chain, as it moves around in its circular path, if you were a point on that chain, you would be traveling with the same linear velocity. So that's going to take us from the sprocket on the pedal to the sprocket on the wheel. I need to figure out then what the linear velocity is of the pedal, because I know that's going to be the same as the linear velocity of the gear. I'm just going to call the back wheel the gear. Well, no, let's not call it the gear. Let's call it the, the wheel sprocket, the WS. How about that? So the linear velocity of the pedal is the same as the linear velocity of the wheel sprocket. Well, the linear velocity of the pedal is going to be 35 revolutions per 1 minute times its radius. What's its radius? 9, right? It says it's 9. So that's 9 inches. So I have 35 revolutions per 1 minute times 9 inches. I'm just going to leave it like that. I'm not going to type that in or anything. I'm just going to store that number. Okay, so now that I have the linear velocity of the back wheel, or the back sprocket, the angular velocity of the back wheel sprocket and the tire itself are different. Or are they the same? What do they have in common? Let me ask that question. The back wheel and the back wheel sprocket, do they have the same linear velocity? No, they have the same angular velocity, right? Because they're on the same axle. So now, let's go ahead and figure out the angular velocity of the wheel sprocket. So using the same formula, the velocity of the wheel sprocket is going to equal R of the wheel sprocket times omega of the wheel sprocket. So if I solve, oops, sorry, my letters here are getting messed up. If I solve this for the angular velocity is just going to be V divided by R. So the angular velocity of the wheel sprocket is its linear velocity, which is now 35 revolutions times 9 inches divided by 1 minute divided by the radius. Well, what's the radius? It's 3, right? So if I divide that by 3, that's like putting another factor of 3 in the denominator. So notice all I did is I took the angular velocity, I multiplied it by 9, and now I divided by 3. That's what we call a gear ratio, right? The gear ratio is 3 to 1, essentially. All right, so now that this number right here gives me the angular velocity of the wheel sprocket, I know that that's the same as the angular velocity of the tire because they share an axis, right? And now that I have the angular velocity of the tire, I can plug it in right there. So here we go. Now the velocity of the tire, which is going to be the same as the velocity of the bike, which is what I'm after, is going to be the radius of the tire, which is 29 inches, times this number right here, which is 35 revolutions times 9 inches all over 1 minute times 3 inches. And notice I'm keeping all of my units intact because in the end I want my answer to be in miles per hour. So let's see what units I have right now. My inches here, divide out, but I'm still left with inches revolutions per minute. And so now let's convert that to miles per hour. All right, let's do time first. I've got minutes in the denominator, so I want minutes to be in the numerator, so they divide out. And I want hours to appear. So 60 minutes is 1 hour. Minutes divide out. And now I have hours. And now I need to go from revolutions. Let's get rid of revolutions. 1 revolution in the denominator is 2 pi radians. And again, this is the conversion factor that most students forget about. Revolutions now divide out. And now we have radians, which are unitless. So now I have inches per hour, which is better. And then the last little conversion factor, since that's 29 over 1, I want inches to divide out in the bottom, and I want miles to appear. Well, I need to go through feet. So 1 foot is 12 inches. So now your inches divide out. And then the last conversion factor here, we want feet to divide out, and we want miles to appear. So as I told y'all yesterday, 1 mile is how many feet? 5,280. Good. You're learning all of these nice numbers. All right, so now if you take inventory on your calculation, if you look in the top, you have radians times miles, which is just miles. And on the bottom, you have hours. That's it. So notice, it looks like it's pretty complicated, but everything in purple is just conversion factors. All we really did is the following. Look, we took our original 35 RPMs, we multiplied it by 9, which was the radius of the pedal sprocket. We divided it by 3, which was the radius of the gear, or the back wheel gear, and then we multiplied it by 29, which was the radius of the tire. So we multiplied, we divided, and we multiplied. That's all we did. And that's the gear ratio aspect of it. So now with all of these numbers laid out, and I know y'all do a lot of this in your science class, namely chemistry, you could just type in all of those numbers, forgetting about the ones. So very carefully here, I'll go from left to right. I've got 29 times 35 times 9 divided by 3, you could do it that way, times 60. It's our final answer, so we'll go ahead and multiply by pi, so by 2 pi. We're dividing it by 12, and then we're dividing it by 5,280. So that right there, it looks like we've got all the numbers. You end up with the velocity of the bike equaling 18.117 miles per hour. And that one, it does make sense to put 3 decimals because those were accurate numbers that we started with. Okay? So that's a nice problem because we're transferring, not energy, but we're transferring quantities from one to another. The linear velocity of the pedal gear and the wheel gear are the same. The angular velocity of the wheel, the tire itself, and the tire sprocket are the same. All right? So any questions on that? That's the last one. It's a good problem. I think there's one like that in the worksheet. I hope there is. All right, so practice. The worksheet we do tomorrow. We'll quiz tomorrow. I'll probably give you a question. I might give you some like the last quiz, like the ones we've been warming up with, just to make sure y'all still know how to do that. And then I'll probably give you either a question like the bicycle problem here or the problem like number 8 where Mrs. Lincoln is rolling through the park. All right, so pretty much anything from the notes of the worksheet. Are there any questions before we conclude the lesson? All right, so with 6 minutes left, I'll give you the rest of the period to work on your worksheet rather than start the next section. But we will move on to the next section tomorrow, 5.3. We're starting to get into the SOHCAHTOA stuff now, which are applications of the angles.